Now in the next part of the paper, Einstein takes up the challenge to prove that this constant h is greater than 0. But as I said, we have to prove this because it is not clear from this expression. In order to prove this, Einstein considered a theorem in mathematics. Now we will prove this theorem as well. The theorem states that if we consider phi of x, and phi of x is a homogeneous quadratic function, which means that if we have phi of some constant a times x, this is equal to a squared phi of x. Then if we define z of y like this, integral over some coordinates dx1 dot 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 dxn, and we integrate over a constraint phi of x, and by phi of x in this case we mean phi of x1, x2, xn. So in this case x can be x1 dot 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 xn. It's a function that goes from Rn to R because it outputs a scalar, and phi of x here is greater than or equal to y, less than or equal to y plus delta. We will show that if we define a parameter a greater than 1, it's a real number greater than 1, then we can prove that the ratio between z of y of a squared and z of y is equal to a to the 2 minus n, and if we choose n greater than 2, this is less than 1. This is an important inequality that Einstein considered in his paper. We will prove this, and this is important because this means that z of y over a squared is less than z of y, and it means that z of y is an increasing function if we increase its arguments, because 1 over a squared is less than 1. If this is true, Einstein argued that omega prime here, this is a derivative, and it is the derivative of this kind of integral here. So we are integrating over a region, and the integral is very similar to this one, where instead of y, you have to consider the energy. So we are integrating over a constraint that considers a function phi of x to be enclosed between some energy and some energy plus a small increment. So if we prove this theorem here, we are able to say that omega prime of e is greater than 0. And of course, since we are integrating over a region, over some space, over some hypervolume, if you want, omega of e is also greater than 0. So this is why this theorem is important. If this is true, then Einstein argued that the derivative of omega of e is greater than 0. Let's try to prove this. So integral over dx1 dot 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 dxn, y less than or equal to phi of x less than or equal to y plus delta. If we change variables, so we go to xk equal to a x prime k, where k can be equal to 1, 2, all the way up to n. This will give us a to the power n integral over dx prime 1 dot 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 dx prime n. And the constraint here can be rewritten like this. Since phi of x is a homogeneous quadratic function, we can rewrite it like this: y over a squared less than or equal to phi of x prime less than or equal to y plus delta over a squared. And this is equal to a to the n, then integral. When we integrate over the first variable x1 prime, we will have some function that I will call f, and f will depend on x2 prime, it will not depend on x1 prime anymore, dot 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 xn prime, but it will also depend on y plus delta over a squared minus f x2 prime dot 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 xn prime, and then here we will have that this function depends on y over a squared because this is the first bound, and then we have to integrate over dx2 prime dot 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 dxn prime. Now, since delta is a very small quantity, in this case we will let delta over a squared go to 0. If we let delta over a squared go to 0, this difference here will become a differential. So we can rewrite this in this fashion: a to the power n minus 2, so let me show you why, integral of the derivative of f, which depends on x2 prime dot 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 y over a squared, and then here we take the derivative of this function with respect to y over a squared. Then we multiply by delta, because we let delta go to 0. And in principle here we should multiply by delta over a squared, but I have put 1 over a squared here. And then we multiply by dx2 prime dot 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 dxn prime. And this is the first result that we get if we change coordinates. If we didn't change coordinates here, we can also rewrite that integral in a similar fashion, but like this. It would be integral of derivative of f of x2 dot 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 xn, then here we have y, then here we divide by dy, so it's the derivative of f with respect to y, delta dx1 dot 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 dxn. This integral here is simply z of y, because it is the integral that we started with, whereas if you take a look at it, this integral here is just z of y over a squared. So we have shown that z of y is equal to a to the n minus 2 z of y over a squared. And this basically means that z of y divided by z of y over a squared is equal to a to the n minus 2. And if n is greater than 2, this is greater than 1. So we have shown that if we have more than 2 coordinates, this function z of y, which is related to that integral, is an increasing function if we increase its argument. And this is the way Einstein argued that omega prime of E should be greater than 0. And therefore, h should be greater than 0.